Today we are going to see time domain analysis or time response analysis. In control systems, we will analyze the system in two ways. One is by using frequency. We will do in frequency domain. That is in Laplace domain, we will analyze. Another one is we will analyze in time domain. That we are going to see now. Time domain analysis. Time response analysis or time domain analysis. That we are going to see. Time domain analysis. First, we must know that what is time response? Time response. Time response means the response of the system or output of the system. Both are same, one and the same. The response or output, both are same. Time response of the system is the output of the system as a function of time. If you plot the response, the output as a function of time versus magnitude, then it is called time response. We are plotting between time. At 0, the time we are giving input means, suppose the response is like this, then it is called time response. It is called time response. Time response means output of the system for a given input. For a given input. Output of the system for a given input with respect to time. Output of the system for a given input with respect to time. That is called time response. Here, various time responses are given. Various time responses are given. If you see the first response, this is the first response. Time is 12 seconds, 0 to 12 seconds. At the 0th time, the input is given, say step input. That's why it is called step response. Why it is called step response? The input is step input. What is step input? What is step input? Step input means you are giving step input to the lamp. You are giving step input to the fan. Initially, what is the value? Applied voltage to the fan, 0 volt. After that, what is the voltage? 230 volt. So you are giving a step input. You are giving a step input. This is time. This is time. At 0 time, t equal to 0, you are applying a voltage of 230 volt. It means you are giving a step input to the system. In this case, system is fan, or system is tube light, or system is some lamp. For that, you are giving a step input. So it means a constant input is given at t equal to 0. That is called step input. For that, if the system gives some output, means that output, the plot of the output between time and magnitude is called step response. That is called step response. So step response means the system's output for step input. The input may be magnitude. The input magnitude may be vary from one value to another. For example, in your fan, you are giving a step input of magnitude 230 volt. The magnitude is 230 volt. In this case, unit step input. Unit step input. Generally, we will give unit step input. Unit step input we will give. Unit step input means the magnitude is unity. The magnitude is unity. At t equal to 0, it will be raised from 0 to 1. This is step in, unit step input. At t equal to 0, the magnitude equal to magnitude, that is input x equal to 1, remains 1 up to infinity. Up to infinity remains 1. That is called step input. Step input. Unit step input. Such unit step input is given Unit step input is given. Its response is plotted here. Its response is plotted here. Input is this. Input is not marked here. The red line is input. Unit step input. For that, the system is also going to that value 1. It follows the step input, but after some time, that is called sluggish response. Sluggish response. You already at t equal to 0, you gave input 1. You gave input 1. At t equal to 0, you gave input 1. But the system output is like this. It reaches 1 after some time. It reaches 1 after some time. That is natural. That is natural. It cannot follow with the input. Is it possible? Suppose I am giving input to a system. It has to respond for that input. Then only the output will come. After some time only it will come. That's why the response gradually increases and finally it reaches 1. So we can call this as sluggish response. Why? It takes a long time to reach the final value. It takes a long time to reach the final value for a step input. Another response is there. This is second response. This is first response. This is first response. That is sluggish response. You follow my pen. The second response. The second response is this. The second response is this. That is somewhat better while compare with 1. It is not sluggish. It is slow response. It is slow response. The second one is slow response. Second one is slow response. The third one is further quickly it reaches final value. It reaches quickly to the final value. Smartest response. Smartest response. Smartest response. Smartest means superlative degree. That's why it should follow input. That is ideal case. That is not possible. That is ideal case. If it that is the smartest. If it input and output are same, then that is smartest. But here that is the maximum possible. That is third case. That also reaches the final value as quickly as possible. We'll compare with 1, 2. It is faster. Quickly it reaches final value. All the 3, the difference is this is fast. This is fast. Third is very fast. 2 is slower. First is sluggish. Sluggish. Second one is slow. Third one is smartest. Another system is there. If you give input, it reaches beyond the final value. For example, 100-meter race. Are they stop at 100 meters? No, they are crossing 100 meters and running. It's not possible to stop at that point. Why? It's not possible to make the speed. Suppose they are running at some higher speed. They cannot make the speed at 0 immediately. That's not possible. Gradually they can reduce. That's why it reaches very fast. It comes vertically, no, very fast. It reaches the final destination, but it cannot stop there. That's why it goes beyond that value, then come down again the same velocity. Because of that, it oscillates, finally settles. Finally settles. You can notice whether you attended electrical lab. Notice that indicating instruments. In that, if you connect it, oscillates and finally settles. Poor damping systems will oscillate indicating instrument, not digital instrument. Nowadays, many are using digital instruments. But indicating instrument needle will go beyond that value, then come back again. It oscillates, finally it settles. That is the example. If you plot that response, it will be looking like that. Suppose I am connecting a 230 volt to that indicating instrument. How much I gave? Step input of 230 volt I gave. That meter goes beyond 230, then come down and oscillates. Finally, it settles at 230. So this is the response of that indicating instrument. Indicating instrument that oscillates for given input. That oscillates for given input. This is quick response. Response is quick, but it comes to final value quickly. No, it oscillates for some time, then finally it settles. Fourth response, quick and less oscillatory. Less oscillatory. But fifth response, if you see that, it very quick and oscillatory. Very quick and oscillatory. Because speed is higher, that's why it quickly reaches the final value, but it cannot stop there. That's why it goes beyond that, then oscillates around that and finally settles. So there are 5 types of response. Sluggish response, slow response, smartest response, that is the maximum possible way. Then quick and less oscillatory. The fifth one is very quick and oscillatory. Very quick and oscillatory. There are 5 types of step response. Why it is called step response? The input is step input. For that, how the system behaves is step response. Both are step responses. What is the difference? The first one is sluggish. The second one is smart. Smart, but it oscillated. Why I am saying that it's smart? It reaches the final value quickly. At what time? Say at 1 second it reaches final value. Here, this is first time reaches the final value at 5th second only. Which is smart? The second one is smart. Because it reaches the final value quickly. In 1 second it reaches the final value. But it is oscillatory, that is different. It is oscillatory, that is different. But it has quickly it reaches the final value and oscillates around that value and finally settles. This transient part, this is called transient part. It is varying, it is not fixed. Varying. Finally it reaches final and it remains there. That's why after this part is called steady state region. Steady state region. After this, before that it is varying. It is varying. Before that it is varying. That's why it is called transient. It is moving. That's why it is called transient response or transient region. Up to this, the response is called transient response. After that, it is called, it remains steady. In the indicating instrument in the lab, you might have seen, if you connect a 230 volt to the indicating instrument, it oscillates. Finally, it settles at 230 and remains at 230 only. Once it settled at 230, then the response is called steady state response. That is called steady state response. Before that, it is varying. That's why it is called transient response. So the response can be divided into 2 parts. One is called transient response. This part is called transient part. Transient response. This is steady state response. So response can be divided in 2 parts. This part is called, once it becomes steady, then it is called steady state response. Before that, it is varying. That's why it is called a transient response. Here also, up to this point, it is varying. Up to this point. Smart system, up to this point, it is varying. That's why up to this point, it is called transient response. Transient response. This part is called steady state response. After this, it is called steady state response. You understand this? Input. There are various types of inputs are there. The input may be a impulse input. Step input, already I explained what is step input. Step input means at t equal to 0, it will rise to a particular magnitude or remains in that value. That is called step input. Impulse input means at t equal to 0, you are giving input Afterwards, its magnitude is 0. Before and after t equal to 0, its magnitude is 0. Can you give any example for impulse input? Mechanical example. Impulse input. Impulse input. Hammer blow. Hammer blow is an impulse input. Your hammer blow you are giving means at t equal to 0, the energy content in the hammer is transferred to that body. At t equal to 0. After that, no input. After that, no input. Hammer blow is an example. That is called impulse input. Impulse input. At t equal to 0, its magnitude is goes up to infinity. Ideal case, its magnitude goes up to infinity. But if we integrate that signal, from minus epsilon to plus epsilon, that signal is called del of t. That signal is called del of t. Del of t. That signal, del of t dt. That signal is if we integrate this, its magnitude will be, if we integrate the signal, impulse signal, del of t is impulse signal. If we integrate this, its value will be unity. Unity, 1. Unity means 1. Or we can say A. Hammer blow. What is happening there? What is happening there? Energy in the hammer is transferred to that body. So, some energy is transferred from one body to another body. Energy is transferred from one body to another body. Here, the ideal case, its magnitude is infinity. Its width is 0. Its width is 0. Is it possible to have width of 0? Limiting case of 0. Limiting case of 0. Its magnitude is, its width is tends to 0. Width tends to 0. Similarly, height tends to infinity. Tends to infinity. Mathematically infinity. Width is mathematically 0. But is it possible to have a width of 0? Not possible. Ideal case. Width of 0. At t equal to 0, the energy is injected. If you draw the signal, I can draw this much duration. Hammer blow will be, sir, 10 millisecond. Hammer blow, how long it will be in touch with another body? The hammer blow, maybe 10 millisecond. 10 millisecond. Height is, say, height is A. Its width tends to 0. If width tends to 0, this magnitude will go to infinity. That is the meaning. If the width tends to 0, the magnitude goes to infinity because this is the fixed area. Fixed area. If it goes on decrease the width, what will happen? The height will goes on increase. If it goes to 0, definitely height will go to infinity. That is the meaning. That's why Bruce Lee becomes famous, because the point of duration of contact is very, very less. The duration of contact is very, very less. That's why his impact is very high. Impulse input. He is giving impulse input. That's why he became famous. The time of contact, the blow same, but time of contact is very less. That's why he became famous. So this is called impulse input. As width decreases, magnitude goes on increases. That's why this signal we cannot talk in terms of magnitude, impulse input. Energy content, we have to talk in terms of energy content. That's why integral of del of t from minus epsilon to plus epsilon. This is epsilon, minus epsilon to plus epsilon. This epsilon tends to 0. epsilon tends to 0, its the energy content equal to A, then it is an impulse signal of magnitude A. Impulse signal of impulse input of magnitude A. Interchangingly, we will say input signal. Actually, here input energy. In control system, input is energy. That's why we can say input. Simply say input. Input signal also we can say it is not signal, actually energy. So the magnitude is A. The impulse function's magnitude is A. If you integrate, you will get A. Because you are getting the area of this area you are finding. Integration means area. Suppose I am having a signal like this. If you integrate this signal, what you will get is, this is a signal. If you integrate this signal up to t, 0 to t, if you integrate that signal is x of t. X of t is varying like this. If you integrate this signal, what you will get? Up to t, you will get area under this curve. So similarly, that is energy content. Here, you are finding the area by integrating this, but the epsilon tends to 0 because the signal is available only at t equal to 0. Not at other points. It's not available. So its magnitude is A. Therefore, it is an impulse signal of magnitude A. Then unit impulse means A equal to 1. If A equal to 1 means it is unit impulse signal. Unit impulse signal. That's all. Step signal means its magnitude is A at t equal to 0 and remains A forever. Remains A forever. Then it is called step signal. If the magnitude is equal to unity means unit step signal or unit step input. In control system, we won't use the signal word. Unit input, unit step input, unit impulse input. Like that we will say. Okay. That is called step input. If we take Laplace transform of this, Laplace transform of del of t equal to 1. Laplace transform of unit impulse signal whose magnitude is A means Laplace transform will be A. Laplace transform of unit impulse signal means unit impulse input means its value is 1. Its value is 1. So Laplace transform of del of t equal to 1. If it is unit impulse input, Laplace transform of del of t equal to A if its magnitude is A. If its magnitude is A. That's all. Laplace transform of step input. Step input is normally represented by u of t. You might have studied in signals and system. U of t. U of t. If you find the Laplace transform of u of t, it's equal to 1 upon s. 1 upon s. If its magnitude is 1, if its magnitude is A means Laplace transform of u of t equal to A upon s. A upon s. So if you find the Laplace transform for that signal, it will give 1 by s, unit input. If it is magnitude A, step signal means A upon s. A upon s. You understand this point? So in frequency domain also we must know. Frequency domain also we must know. If you time domain, how u of t looks like in time domain? Time domain, it is looking like this. In frequency domain, it is 1 by s. In frequency domain, it is 1 by s. Already I told you that time and frequency are inversely proportional. That's why that infinity becomes 0 here in time domain. Time domain 0 becomes infinity in frequency domain. They are inversely proportional. Inversely proportional. You have to imagine like that. You have to imagine like that. So u of t, time domain, if you plot that unit step signal, it is looking like this. Time versus magnitude. If you take Laplace transform of unit step input, you will get 1 upon s. Impulse response, if you take Laplace transform, you will get 1. Unit impulse means impulse of magnitude A means you will get A. The third signal, ramp signal. The third signal is called a ramp. Ramp, it is like a ramp signal. Ramp input or signal. In control system, we used to say input, ramp input. It is like a ramp. It is go on increases up to infinity. Go on increases up to infinity. Time versus magnitude. Time versus magnitude. Ramp signal. Its slope, if its slope equal to 1 means unit ramp signal. Slope equal to 1 means what? At 1 second, its magnitude will be 1. At 2 seconds, its magnitude will be 2. At 3 seconds, its magnitude will be 3. If it is increasing like that, at 45 degree, if it increases, then it is called unit ramp signal. Unit ramp signal. A ramp signal of magnitude A means its slope is A. Its slope equal to slope is A. At 1 second, its magnitude will be A. At 2 seconds, its magnitude will be 2A. At 3 seconds, its magnitude will be 3A. Like that, it will increase. That is called ramp signal of magnitude A. If we take Laplace transform of that ramp signal, A upon S square. If we take Laplace transform of ramp signal, A upon S square. Another signal is called parabolic signal. Parabolic signal. The third signal is called parabolic signal. It is increasing like exponentially. It is like not exponentially, parabolically it increases. That is called parabolic signal. That is proportional to that signal x of t is proportional to t square. Ramp signal, if you see that, it is proportional to x of t is ramp signal, proportional to t. As t increases, it linearly increases. It linearly increases. That's why it is straight line. Linearly increases means straight line, Linear means the graph must be a straight line. That's why it is a straight line. U of x of t is proportional to t. If x of t is equal to t means unit ramp signal. Unit ramp signal. X of t equal to a means ramp signal of magnitude a. Ramp signal of magnitude a. If x of t equal to t, here coefficient is 1, 45 degree. As time increases, magnitude go on increases. Go on increases. At 1 second, its value is 1. At 2 seconds, 2. Then it is called x of t equal to t. So here, if you see the parabolic signal, x of t is proportional to t square. X of t equal to t square means unit parabolic signal. Unit parabolic signal. X of t equal to a t square means parabolic signal of a magnitude a. Normally, to have a convenient discussion among time domain and frequency domain, we will take a by 2. We'll take a by 2. If we take Laplace transform of this, you will get 2 by s square. You will get. If we take Laplace transform of a t square, you will get 2 by s square. 2 upon s square you will get. To cancel that 2, normally we will take a by 2 t square. Magnitude will be taken a by 2 times. So in Laplace domain, x of s equal to a upon s square. We won't discuss a by 2, but that is the meaning. Magnitude of a is, while compare with ramp signal, it is half of the value of magnitude. That way we'll take a upon s square. A upon s square. Sorry, this is for ramp cube. Parabolic a upon 2 by s cube. If you take Laplace transform of this, 2a by s cube you will get. 2a by s square. If you take a by 2, 2 getting cancelled, that's why a upon s cube you will get. Convenient to discuss in both the domain. Because a is unknown. It can be taken any magnitude. A upon S cube for parabolic signal. So now we can Laplace domain in time domain and Laplace domain will write all signals. This is time domain. This is Laplace domain. This is x of t. Impulse first. Impulse signal. Impulse signal is what? Del of t. We'll write like then del of t. In Laplace domain 1, step u of t equal to, if it is unit, all signals we will discuss only unity. U of t equal to t, equal to a, magnitude is 1, u of t equal to 1. Unit step input means u of t equal to 1. If you take Laplace domain, it becomes 1 by s. U of t equal to 1, always the output is, the input is 1, magnitude is 1 forever. From t equal to 0 to infinity, if it is 1 means u of t equal to 1. If you take Laplace transform, you'll get 1 by s. Ramp signal. Ramp signal means x of t equal to t. If we take Laplace transform, 1 upon s square. Parabolic input. Parabolic input. X of t equal to t square. T square 1 by 2 t square. To cancel that 2, 1 by 2 t square in time domain. That's why in frequency domain you will get 1 upon s cube you will get. 1 upon s cube you will get. That's all. If you know, these are the 4 standard signals will be applied to any system to discuss about characteristics. Suppose I want to test you, what I will do? Some input has to be given. Here the input is teaching. How you are responding in a test, that is the output. So I can find the behavior, characteristics of that system. We can study like that. There are many inputs are there to study about a system. The impulse input we can give and how it behaves in time domain. That is called the impulse response. We can study the characteristics of the system. We can give step input, we can study the characteristics of the system. We can give ramp input, we can study the characteristics. We can give parabolic input, we can study the characteristics. There are 4 standard types of input signals that we can give and study the characteristics of the system. You understand this? Most of the time we will apply only impulse and step. Rarely we will apply ramp and parabolic. Another signal we will apply, that is sinusoidal. Sinusoidal. Sine input. Sinusoidal input will apply to the system. If you want to do frequency response analysis, we will give sinusoidal input. That also we will see later. For frequency response, we used to give sinusoidal input. Varying input, but constant amplitude, but signal, constant maximum amplitude, but amplitude is varying like sinusoidal sine signal. That also standard signal. So what are the standard signals? Impulse, step, ramp, parabolic, and sinusoidal. In frequency domain, we will study about sinusoidal signal. In time domain, most of the time we will study about impulse and step only. Transfer function. Transfer function. Already we studied. We found a transfer function for a given system in first unit, but not that. We do not know what is the meaning of that. Transfer function means we used to represent by G of S. Suppose I am having a system. This is the system G of S. I am representing the system by G of S. I am giving input. I am giving input R of T. R of T as input. The system responded for that R of T as C of T. C of T. Output is C of T. Input is R of T. It may be impulse input, or it may be a step input, or it may be a ramp input, or it may be a parabolic input, or it may be a sinusoidal R of t, some signal. For that, what is the response? Output of the system is C of t. Input of the system is R of t in time domain. In frequency domain, what is the input of the system? R of S. What is the output of the system? C of S. I know the expression for C of S. I know the expression for R of S means I can find the transfer function. C of S upon R of S is the transfer function of the system. That is mathematical model in transfer function representation. The Laplace transform of output upon Laplace transform of input is called transfer function. Laplace transform of output upon Laplace transform of input is called transfer function of the system. Transfer function of the system. So C of S upon R of S is called transfer function. The transfer function is represented by G of S. That's why in block diagram representation, you are putting G1, G2, G3. Sometimes some author used to say H of S also. G of S or H of S. They will represent the transfer function as H of S. We used to represent G of S. For feedback transfer function, we used to represent H of S. But the forward path transfer function also can be represented by H of S. It is up to the author, book's author, to represent G of S or H of S. Already I told you that why G1, G2, G3, many transfer functions are coming for a single system. Suppose the system is represented by 5 differential equations. You will get G1, G2, G3, G4, G5. For each transfer function, each equation, you will get one transfer function. For each equation, there will be one input, one output will be there for each equation. If you write a transfer function for that input output, you will get one transfer function, that is G1. For second equation, you will get one transfer function, that is G2. If you connect all these together, you will get the final system. You will get the final system, that is called block diagram representation. For that, we have seen 2 types of simplification to convert into one transfer function, G of S. I want to combine all G1, G2, G3, G4, G5 into single transfer function, G of S. There are 2 methods. One is block diagram reduction. Another one is signal flow graph representation. Once and for all, it is converted. You will get a transfer function like this. Finally, you will get like this. Finally, you will get like this. This is the transfer function, whose degree is n in the denominator, whose degree in the numerator is m. If the denominator is s means, n means it is actually represented by nth order differential equation. Nth order differential equation. Suppose the system is represented by second order differential equation, means n equal to 2. Therefore, that system is nth second order system. Second order system. Here, m, always numerator degree will be less than denominator degree. Always numerator degree will be less than denominator degree. Always n should be greater than m. Not greater than or equal to, we can say, but all practical system will be n will be greater. N will be greater. If m is greater, it's not physically realizable. Not physically realizable system. That's why if you get numerator degree higher means it is not physically realizable. For example, I can find very good circuit. No one can find such circuit. But I can find mathematically. That circuit works very fine. It takes 0 energy. But a component required in that circuit is resistance of -5 ohm. Mathematically, I got -5 ohm. Is it possible to get -5 ohm physically? Physically not possible. Physically not possible. So all physically realizable systems will have numerator degrees less than denominator degree. So always m is less than m. Always m is less than m. If it is greater means it may not be a physically realizable system. Physically realizable. By looking at the transfer function, we can say that whether it is physically realizable or not. We can say by looking at the transfer function, we can say that whether it is not only this, Many aspects are there that we will see later. So if numerator degree is less than the denominator degree, then it is physically realizable. Another